I'm still excited to tell you about TurboDB, a new distributed database that correctly integrates a single machine database that we replicate to tackle skewed workloads. In a distributed database, front-end client machines receive a user request and translates it into a transaction, which are sets of operations that are executed atomically or not at all. The client sends the operations to the relevant distributed servers, which store the data. These servers run distributed concurrency control protocols to ensure that transactions take effect in an order that satisfies consistency. These servers then replicate the data for fault tolerance using a consensus protocol, for example, Raft. When the transaction successfully commits, the clients then return the results back to the users. Distributed databases enable large-scale applications by scaling capacity way beyond what can fit on a single machine. And when the workload is uniformly distributed, they also scale up throughput. So distributed databases are really great, but they're challenged by skewed workloads, where most transactions access a small subset of hot data. Skewed workloads are prevalent in the real world, for example, in Twitter's Twemcache or in Facebook's Tau. They hurt performance because they lead to contention, where transactions repeatedly abort and retry on hot data, leading to lower throughput and higher latency. Conflicts are exacerbated in any system where data is sharded. The main culprit is cross-node coordination. Distributed transactions inherently require cross-node coordination, forcing them to incur at least one network round trip. Their latency, compared to non-distributed local transactions, is therefore orders of magnitude higher. Under skewed workloads, distributed transactions block each other for orders of magnitude longer than local transactions. However, single machine databases, which are entirely central to a single machine, fare better under skew. This is because they don't require cross-node coordination, so transactions don't incur network latency. This enables two performance multipliers, which are properties of single machine databases that benefit its performance but don't apply to a distributed database. The first multiplier is one-stop execution. Transactions complete in one local stop without contacting other nodes. Their short lifetimes mean that most of them don't really live long enough to contend with each other. This decreases the severity of contention. The second performance multiplier is local concurrency control techniques. These are optimizations that exploit data being local to a single machine. They include database-wide techniques like global timestamps or global shared memory, or optimizations that target local bottlenecks. So for example, the single machine database, MVTL, uses shared lock tables to reduce cross-core communication. But this optimization is not effective on a distributed database, where the dominant bottleneck, network latency, is a bit too large of a target. There exists a trade-off between distributed and single machine databases. On one hand, distributed databases scale capacity, but don't efficiently handle skewed workloads. On the other hand, single machine databases can't support large-scale applications beyond its single machine, but they do efficiently handle skewed workloads. We want to bridge the gap between these two database types to achieve both scalability and good performance on skewed workloads. We build a new hybrid architecture that integrates a single machine database into a distributed database. We use a distributed database to scale out storage capacity and use the single machine database to turbocharge performance with its multipliers. Our core challenge is to bring the performance multipliers of single machine databases to bear on skewed workloads within a distributed database. Our solution is to first replace one of the servers of a distributed database with a single machine database. We designate it the turbo. Then we strategically co-locate the hottest keys on the turbo so they reap the multiplier's benefits. Finally, we shift all cooler keys to the servers. Our key insight is to prevent the turbo from incurring cross-node coordination and thus network latency when executing requests. This precipitates two sub-challenges. The first is a concurrency control challenge. The turbo and distributed database independently run local and distributed concurrency control protocols, respectively. Transactions that access both hot and cool data will see some of their operations committed by local concurrency control on the turbo, and the remaining committed by distributed concurrency control on the servers. Despite this, the turbo and servers must order transactions the same way without forcing the turbo to coordinate with another machine. To address this, we introduce hybrid concurrency control, or HCC. The second challenge is replicating the turbo for fault tolerance without replication latency interfering with the multipliers. To address this, we introduce Phalanx, our turbo-specific custom replication protocol. We first elaborate on HCC, then on Phalanx. Hybrid concurrency control orchestrates both the turbo and distributed database's individual protocols such that they both totally order transactions in the same serial schedule, and they do so without the turbo incurring cross-node coordination. HCC defines correctness as process-ordered serializability, which means that the database appears to have executed transactions in a single serial order, and that order is the same that users submitted transactions in. To enforce a matching order, a transaction is assigned a timestamp. Both databases then execute their parts of the transaction at that exact timestamp. Since both local and distributed concurrency control serialize transactions in timestamp order, they converge on the same total order. That order matches the one that clients submit transactions in, since clients themselves generate the timestamps. To preserve the turbo's performance multipliers, HCC prevents it from incurring cross-node coordination. We run the turbo as a standalone single machine database, unaware of its role in the hybrid architecture. The servers mimic the turbo's intended usage as a standalone database, since if the turbo performed well independently, it'll continue to do so in our architecture. We abstract away the servers as the turbo's single machine database clients and encapsulate each turbo request as an isolated single machine database transaction. Encapsulating requests introduces a transactional atomicity issue. The turbo can't match up multiple isolated requests from the same transaction, yet it must commit them as a single atomic unit. Our solution is to limit each transaction to sending at most one isolated single machine transaction that can read and write, that batches all hot updates to the turbo. We do permit sending multiple read-only isolated transactions. Since these don't modify data, they're correct, so long as they read at a timestamp consistent with the rest of the transaction. The turbo and servers must also unilaterally agree to commit or abort the transactions. But they're not permitted multiple rounds of communication like they would be in two-phase commit. Our solution is that when the turbo commits its isolated read-write transaction, the servers simply mirror that decision. We illustrate how HCC handles general multi-shot transactions, ignoring replication for now. In the execute phase, a client first assigns a timestamp to a new transaction. This enforces process-ordered serializability. The client locally buffers update operations, but sends out read operations, including reads to servers, and read-only transactions to the turbo. To support multi-shot transactions with dependencies, the client sends out round after round of read operations, locally buffering any new updates until every dependency is resolved. Then, the client enters the finale commit phase. It'll divide the buffered updates into cool set and hot sets, and then execute the cool set first on the servers using distributed concurrency control. If the servers commit, or if the servers succeed, they prepare to commit. Only then does the client send the hot set as an isolated read-write transaction to the turbo. The turbo commits that, and the servers mirror that decision. Next, we discuss Phalanx, a custom replication protocol involving only the turbo and no other component. I allied most of Phalanx's details, and instead highlight how it replicates the turbo's data without letting replication latency penalize its multipliers. Building off prior work, Phalanx decouples replication from transaction execution. After committing a transaction, the turbo primary makes it visible to future requests before and while replicating it, buffering the results until replication succeeds. Buffering committed transactions raises a subtle issue. The turbo's performance can't tolerate returning them in assigned timestamp order. This is problematic because not doing so may break correctness. For context, some replication techniques for single machine databases require that the database assign transaction timestamps to correlate with the order that transactions commit on the turbo. Transactions that commit earlier receive a smaller timestamp, while transactions that commit later receive a larger timestamp. Single machine databases timestamp transactions in strictly increasing order, and some of their replication techniques rely on this for correctness. But this is false for the turbo. As part of the hybrid architecture, the turbo receives requests whose pre-assigned timestamps are out of order with their arrival. This is due to network asynchrony and clock skew on the distributed database. Yet, the turbo can't block progress until the smallest timestamp transaction arrives, if one even exists. To correctly return buffered transactions without blocking progress, Phalanx introduces the frontline mechanism. The frontline is defined as a global threshold timestamp that represents a snapshot of the turbo where all committed transactions in the snapshot can be returned without correctness issue. These are timestamped below the frontline. And all transactions not included may not be returned. These are timestamped above the frontline. When returning transactions, the frontline only selectively obeys the timestamp order. That means that transactions are timestamped when transactions are timestamped in increasing order, like in a normal single machine database, the frontline is calculated to move forward, returning more and more transactions. But when a smaller timestamp transaction commits out of order, the frontline moves backwards, just below that transaction's timestamp. That sounds unintuitive, but the frontline's backward movement is correct. It prevents the primary from returning newly committed but unreplicated transactions prematurely. It also doesn't revoke the correctness of previously returned transactions. So long as they're replicated, the transactions and the transactions that they depend upon are also replicated. They remain correct, regardless of the frontline's movements. We built TurboDB on CockroachDB, a production distributed database, and replaced one of its servers with Cicada, a single machine database serving as the turbo. Our baseline is CockroachDB. We run transactional YCSB, TPCC new order transactions, and others under varying skews and read-to-write ratios. In this presentation, we focus on YCSB. Our performance metrics are throughput, latency, and scalability. In our YCSB plus T experiment, we promote the 40 million most popular keys to Cicada in order to leverage its multipliers without oversubscribing it. We plot curves of median latency versus throughput, where lower latency and higher throughput are better. To highlight performance differences, the graph on the right plots throughput versus level of skew. Under uniform workloads, so workloads with no skew, CockroachDB and TurboDB perform similarly, with Cockroach slightly outperforming Turbo. Since high skew is what Turbo targets, it minimally impacts uniform workloads. At medium skew, TurboDB starts showing a performance advantage. And at high skew, TurboDB outperforms Cockroach with both lower latency and an order of magnitude higher throughput. CockroachDB is bottlenecked by contention on its hottest keys, where 1 in 10 transactions are aborting. In contrast, TurboDB leverages Cicada to mitigate that bottleneck, so it achieves better performance. We also plot how well TurboDB horizontally scales up throughput with how much data is being stored, the number of servers being a proxy for that. The dotted line denotes networked and replicated Cicada's max throughput. At high skew, CockroachDB isn't really scaling up throughput. There are too many contending transactions, and the conflicts are exacerbated by increasing amounts of data. In contrast, Turbo scales up throughput until capped by Cicada's max. As a single machine database, Cicada can't scale anymore to support more storage. But TurboDB throughput, when it levels off at the same max, remains capable of scaling storage by adding servers to the distributed database. TurboDB is a new hybrid database for skewed workloads. It integrates a single machine database into a distributed database to both turbocharge performance and scale storage capacity, respectively. To ensure performance and correctness, we introduce HCC to coordinate two concurrency control protocols and Phalanx to make the turbo fault tolerant. We implement TurboDB on CockroachDB and Cicada to demonstrate significantly better performance on highly skewed workloads. Thank you.